Okay, a couple of examples related to infinite series. I hope neither one replicates the video that's already there in the Blackboard folder for this topic, because that one's been there for a while and I didn't actually look to see what was in it because I forgot what I made last year, but I don't think these duplicate it. Like infinite sequences, infinite series for us are sort of a means to an end, in that we acknowledge that they are there, we learn how to do a few things with them, and really leave it wide open to all the potential applications and then things you can use them for in more advanced classes down the line. For example, if you ever take a course in partial differential equations, you're going to use series. If you take more advanced math classes, you're going to use series. If you take a course in complex variables, you're going to use series. So it seems very intermittent in terms of, well, why are we seeing all these sort of random topics about series? And it's really, well, you're just studying them because they are there and you're taking a math class, but also because you need familiarity with them so that they're not a surprise later on. Okay, so a couple of fundamental ideas. One of them we're going to take a look at in the context of this top series, which is the sum of n equals, from n equals 1 to infinity, of 1 minus negative 1 to the n. And I just realized that that n is in the wrong place, because otherwise it wouldn't make any sense. It would just always be 2 to the n, and that's not what I want. Okay, so I've moved the n to the inside of those parentheses. I'm going to illustrate the concept of partial sums. Partial sums are just the rolling summation of terms as you keep adding one more term. So the first partial sum is just the first value of this series. When n is 1, the value of this series recipe is 1 minus negative 1 to the first. 1 minus negative 1 is 2. Right? And then the second partial sum is the sum of the first two terms, which is that 2 plus whatever comes next, which is 1 minus negative 1 squared, or 1 minus 1, which is 0, which is 2. And then the third partial sum is going to be 2 plus 0 plus, okay, now what we get from the third term, 1 minus negative 1 cubed, 1 minus negative 1, 1 plus 1, there's another 2, and that's going to be 4. S4 is going to be 2 plus 0 plus 2 plus, you see we're just adding a new term each time. When n is 4, we're going to get 1 minus negative 1 to the fourth, 1 minus 1, so we're adding a 0, and that's a 4. And so what's happening, you can now predict the results. 2, 2, 4, 4. You can guess the next two are 6, 6. Now these results, 2, 2, 4, 4, that is the sequence of partial sum values. And the convergence or divergence of the series is dictated by the convergence or divergence of that sequence of partial sums. You can see that this sequence, 2, 2, 4, 4, diverges. It'll be 6, 6 next. This diverges. So since the sequence of partial sums diverges, then the whole series diverges. And just as a little food for thought, I will now ask you, what would it happen if I went back and made this a plus? 1 plus negative 1 to the n. I'll let you puzzle that out. Then do you get a convergent series, or does it stay divergent? And what are the partial sums? Okay, second example is to demonstrate whether this series, which is written out term by term, converges or diverges. And this is an example of a geometric series. A geometric series is a series where the terms are just going up by powers of 1 of some central term. So in this case, we have e over pi to the first squared cubed. The first term is 1, but 1 is another word for e over pi to the 0, right? So I'm going to write the second term as e over pi to the first. And I'll write the second term, which is given originally as e squared over pi squared. That's e over pi, the quantity, squared. And then plus e over pi cubed, etc., etc. We can wrap this up into a summation. our counter is going to start at 0, and it's nicely placed as the exponent. This is going to be e over pi to the n. So the sum from n equals 0 to infinity of e over pi to the n. And now we're going to match that to the standard geometric series formula, which is the sum from 0 to infinity a times r to the n. And we've got to decide what's what. Well, e over pi to the n, r to the n. Certainly clear that r is e over pi for us. And a, well, right there's kind of a ghost 1. So a is 1. And the geometric series formula tells us, this is in the notes and the book and everywhere else you look up geometric series, that our series will converge if the size of r is less than 1. Now e is 2.718, etc., etc. Pi is 3.14, so e over pi is most definitely less than 1. So this thing converges. And it converges to, once you've identified a and r, the geometric series, if it converges, will converge to whatever number a over 1 minus r turns out to be. There's an explanation in the notes about why that works. And this will be 1 over 1 minus e over pi, which, if we simplify, will end up looking like pi over pi minus e. I don't know that that's any better than that, but it is what it is. So that will be the value of this infinite series. We have added up an infinite number of numbers and gotten a finite result.